In section 2.2, we're going to work on finding limits graphically and also numerically. For instance, suppose we wanted to sketch the graph of the function f of x equals x cubed minus 1 divided by x minus 1. One of the things that we would know if we look at this function is that wherever the denominator is equal to 0, that is, wherever x is equal to 1, this function is going to be undefined. So x equals to 1 is not in the domain of the function f of x. But ultimately, if we're going to graph this thing, we would kind of like to know what is the function doing near that disallowed value, the one we're not able to plug in. So we look at it and we say, okay, well, we know we're not able to plug 1 into the function. But if we can plug any other number in other than 1 in, let's see what's going to happen. So, for example, you can plug 0.75 in, and what we would see is we would get the output 2.33. Let's now pick a number that's going to be a little bit closer to 1. Say something like, let's plug in x equals 0.9. If we plug in x equals 0.9, we get the output 2.710. And what we're going to do is we're going to continue to do this, plugging in numbers that are closer and closer and closer and approaching this value 1, which is not in the domain of the function. And what we notice is that as our inputs are getting closer and closer and closer to 1, and this is coming in from what we would call the left-hand approach, on the number line, these are a sequence of x's that are successively getting closer to 1 and are slightly less than 1. So this is what we would call the left-hand approach. What we see is that the collection of outputs that we are getting is kind of stabilizing, and then they themselves kind of look like they're getting closer to the value 3. Similarly, we could do the same idea starting over here at, let's see, maybe like x equals 1.25. That certainly is in the domain of the function, so we'd be able to plug that in. If I plug 1.25 into the function, we would get an output of 3.813. Now let's plug in something that's going to be a little bit closer. Let's say like x equals 1.1. It's in the domain of the function. So if I plug 1.1 in, we can get the output 3.310. And we're going to do the same thing. Let's continue to pick values of x that are getting closer and closer and closer to 1. Here, these are getting closer coming in from the right-hand side because all of these numbers are bigger than 1. So we would call this the right-hand approach. And what we see is that the series of successive outputs we get is again getting closer and closer and closer to the value 3. So we would say that it looks like, at least to us, that as x is getting closer to 1 from either direction, that the outputs that we are getting closer and closer to that value of 3. And that is the case. We would write this, the notation for this would be written as follows. It's the limit as x approaches the value 1 of the function f of x would be equal to 3. And graphically, what you would have there is there's actually going to be a hole in the graph. Remember, we can't plug 1 in, so the function is not defined when x equals to 1. But what's going on is that the function values themselves are getting closer, and they're approaching this value of 3, and so we have an open hole in the graph at the order pair 1, 3. So this is one of the things that's kind of nice. This is one approach we can do to find limits of a function, is we can just use what's called a table of values. Again, at the end of the day, for this starting function, the only value of x that was not in the domain was x equals to 1. Any other value we're able to go ahead and plug in. And so the idea is, let's start with a couple of values, and let's let the values get successively closer to 1, and let's see what's happening to the series of outputs we get. If those series of outputs is approaching a fixed number, we usually call that the limit L, then we would say that the function has a limit as x approaches the x value, c, of f of x, we would say that it's equal to L. So in our limit notation, this is how we would write it. We say that the limit as x approaches to c of f of x equals the limit L, means that as x gets closer and closer and closer to c, the function value's outputs get closer and closer and closer to L. And that notion of closeness, what we mean by that, we'll make that a little more precise here in a little while. Let's take a look at one together. So in example one, they ask us to evaluate the function f of x equals x divided by the square root of x plus 1 minus 1 at several values of x near 0, and then use the results to estimate the limit. Okay. Again, for this function, if we were to look at it, when is this denominator equal to 0? Well, if we have the square root of x plus 1 minus 1 equals to 0, we could bring the 1 over to the other side. We have the square root of x plus 1 equals to 1. Square both sides. We have x plus 1 equals 1. Subtract 1 from both sides, we get x equals to 0. So that value, x equals to 0, is not in the domain of this function. So we're not able to plug 0 in and get an output. Nevertheless, we would still like to know, well, what's the function doing in and around that disallowed value 0? So here's 0 on a number line. It's not in our domain, so I'm going to leave that with like an open circle. Let's choose a sequence of values that's going to approach 0 not only from the left-hand side, but also from the right-hand side. For instance, if I plug, let's say, negative 0.1 into the function, this is something you can easily do with a calculator, we would get negative 0.1 divided by the square root of negative 0.1 plus 1 minus 1, when we just simply take that and plug it in, and we would get an output of about 1.94868. Okay. So that's our output. Let's choose a number now that's still on the left-hand side of 0, but it's going to get even closer. So something like negative 0.01. If we plug that in, we would get 1.994987. And I'll do this one more time. I'll pick one more value that's even closer, negative 0.001. It looks like we're getting the output about 1.999499. So again, these series of outputs, they're all kind of close together, but even more so, they are kind of stabilizing. It looks like they're getting close to 2. Let's see what's happening on the right-hand side. On the right-hand side, let's start with, let's say, something like 0.1. If I plug 0.1 into the function, we would get about 2.0488 as the output. Pick a value that's closer to 0, still on the right-hand side. If I plug in about 0.01, we would get out 2.004988. And I'm going to choose one value, one more that's even closer to 0, something like 0.001. And we get the output 2.000499. So we observe the same kind of pattern here as well. The closer we get to 0, either from the left-hand side or from the right-hand side, it looks like those function values are approaching the value 2. And so the way we would represent this, we would say that the limit as x approaches to 2 of f of x, not as x approaches to 2, x is approaching to 0. The limit as x approaches to 0 of f of x, the function values themselves are getting closer to the output 2. So one of the things that's nice about this method is that this will always allow us to get an answer. So it's not the most clean method. I mean, it kind of revolves a lot of calculations, but nevertheless, it's always kind of something you have as a fallback, where when in doubt, if you don't have no other way to proceed, you can always do a table of values and look at the two-sided approaches if you need to determine a function's limit. Again, graphically, if we want to kind of reaffirm what we just saw, we know that 0 is not in the domain of this function, so there's not going to be a point there. But what we saw is that as we get closer to 0 on the x-axis, those function values were getting closer and closer and closer to the value 2. And so this function's graph would actually have a hole on it at the order pair 0, 2. One of the fundamental things that's extremely important as it pertains to limits is that notice that the function was undefined at 0, and yet we still have a limit as x approaches 0. This often happens, and it's very important to realize that when it comes to the limit does not have anything to do with what's actually happening to the function at the point. It's only talking about what's happening as you approach the value x equals to c from the left and from the right hand side. The function may have a value there, it might not. It could even have something goofy where the value is defined elsewhere, but the limit is independent of what's actually happening specifically at the point x equals to c. Let's take a look at example 2. They say to find the limit of f of x as x approaches to 2. So we're asked to find limit as x approaches to 2 of f of x. This function is a piecewise defined function. We can kind of go ahead and graph it. Notice that for all x is different from 2, so on the x-axis here's 2, we have the constant function 1. So this graph is going to be at a height of 1 for all x except 2. And then what's happening is exactly when x equals to 2, it's going to be the point 2, 0. And maybe just to kind of help it distinguish from the axes, let me go back and color code this function in green so we can all see it. So we're asking what is the limit as x approaches to 2 of f of x? Well, if we approach 2 coming in from the left-hand side, if you think about it from like the output kind of point of view, like we did with a table of values, if I plug in values that are getting closer and closer and closer to 2, this function is always consistently giving us the output of 1, because f of x is equal to 1 for all x not equal to 2. And similarly, if we approach 2 coming in from the right-hand side, if I pick some sequences of values that are getting closer and closer to 2 coming from the right-hand side, we're still getting that same consistent output of 1 there. So we would say that the limit as x approaches to 2 of f of x would be equal to 1. Because that's how the function is behaving nearby x equals to 2. Notice that the actual value of the function at 2 itself, the function has the value 0 there. But that's not the same thing as the limit. The limit is independent and does not have any influence on what actually happens at the point. We're only asking what's happening as our x values get closer and closer to that value 2. In general, not every function will have a limit as x approaches a set value c. So there's situations where limits can fail to exist. 3 of the key behaviors that will prevent a limit from existing is if we have different left-hand and right-hand behavior. So it's possible that maybe the function will approach one value from one direction on the x-axis, and then maybe a different value coming in from the other direction on the x-axis. So if you have different right-hand and left-hand behavior, that's a situation where the limit will fail to exist. If the function has a vertical asymptote at x equals to c, where the function becomes unbounded, then that will also prevent the limit from existing. And a third case that we won't see of as much in this class, but it's also possible that maybe the function oscillates infinitely between some values, and it never actually settles on approaching one value at all. That can also prevent a limit from existing. In example 3, we're asked to show that the limit as x approaches to 0 of the absolute value of x divided by x does not exist. This is yet another example of a function where it's not defined at x equals to 0 because we would have division by 0. This is also a good point to kind of recall and remember the piecewise defined nature of the absolute value of x. By definition, the absolute value of x is equal to x when x is greater than or equal to 0, and it's negative of x when x is less than 0. So what does that mean for this function, the absolute value of x divided by x? Well, it's going to be equal to x divided by x, which is equal to 1 when x is greater than 0. Again, I can't put the equals bar here because we're not allowed to divide by 0. And it's going to be negative x divided by x, which is negative 1 when x is strictly less than 0. So if we were to go in and graph this function, here's what we would notice. Here's 0. The function is not defined for 0. When x is greater than or equal to 0, we get like the constant output 1. So it's like a horizontal line there. And when x is less than 0, it looks like the constant function negative 1. From the graph, we can kind of see why the limit does not exist. So when a limit does not exist, you can just abbreviate it DNE for does not exist. But what's happening is if we look at the limit as we approach 0 coming in from the left-hand side. So as we approach 0 from the left-hand side, the sequence of outputs we get, we would be getting the output negative 1. However, if we approach 0 coming in from the right-hand side, those sequence of outputs we get would consistently give us the output positive 1. So the function is giving us two different sided limits. If we approach from the left-hand side, it's always negative 1. If we approach from the right-hand side, it's positive 1. So it's not agreeing on like one mutual value. You get two different sided limits, and therefore the limit as x approaches 0 in general does not exist. In example 4, they want us to discuss the existence of the limit x approaches to negative 1 of 1 divided by x plus 1 squared. This as a function, this is one that maybe you memorize, is the graph of 1 over x squared. The graph of 1 over x squared looks like this. Either using technology, you could certainly use a graphing applet. This one here would be a transformation of it. Adding 1 on the inside would simply take this entire graph and shift everything 1 unit to the left. So we have a vertical asymptote here at x equals to negative 1, and the function's graph would look like this. So what's happening as x approaches negative 1? Again, you should always look at both a left-hand and right-hand approach to see what's going on. But graphically, if I approach negative 1 coming in from the left-hand side, the closer we get to negative 1 coming in from the left, these function values get larger and larger and larger. The function is approaching positive infinity because of that vertical asymptote we have there. Likewise, as we approach negative 1 coming in from the right-hand side, the function values are again getting larger and larger and larger without bound because it's approaching positive infinity. And so we would say that this limit does not exist. As x approaches negative 1, the function values are approaching positive infinity. They're not approaching a fixed real number L. Another more exotic example of a limit that fails to exist is the limit as x approaches to 0 of the sine of 1 over x. From the graph, what we can see is that as we approach 0 from the left-hand side, the closer we get to 0, this function starts oscillating infinitely often between negative 1 and positive 1. And you can keep zooming in, and the more you zoom in, the more you're going to see it keeps oscillating back and forth, back and forth. It's not approaching any one number, it just keeps bouncing back and forth, so the limit is not going to exist. Same thing happens from the right-hand side. The closer you get to 0 coming in from the right, this function oscillates back and forth, oscillating between negative 1 and positive 1, so this limit does not exist. So again, those are the three common types of behavior associated with non-existence of a limit. You have a different left-hand side or right-hand side approach. If the function becomes unbounded as x approaches c, or if the function oscillates between two fixed numbers and it doesn't decide to approach one number That's another reason why the limit fails to exist. Okay. So in all of this talk about the limit as x approaches to f of x, right, it's kind of saying, well, as x approaches or as x gets closer to c, the function values and the outputs get closer to this number L. So we need to make the notion kind of precise. What does it mean for f of x to become arbitrarily close to L as x approaches to c? And what that means is that you can get f as close to L as you like within any level of precision by taking x sufficiently close to c. Okay. This brings us to what's referred to as the epsilon delta definition of a limit. So the proper definition of what this limit means. The limit as x approaches to c of f of x equals to L means the following. For each epsilon greater than 0, in other words, no matter how close you want my function values to get to this limit, I can make f of x, the difference between f of x and L, as small as I like by taking x sufficiently close to c, meaning there exists a delta such that if the difference or the distance between x and c is less than delta, then the difference between f of x and L will be less than epsilon. This is the classical epsilon delta definition of a limit. We will not be using this as a focal point in our class, but just be aware that that notion of arbitrarily close or how close is properly well defined in the context of the epsilon delta definition of a limit.